Welcome back, everybody. The topic this week and also next week is going to be about autoencoders. Now, autoencoders is a very, a very, very interesting method. And it's going to be, in a certain sense, the first unsupervised method which we encounter. We are going to try to catch at least two birds with a stone here, actually three. So one is obviously to introduce autoencoders, which have been very popular both for regression type of problems and for classification type of problems. But it has also a very nice link with something which is called principal component analysis. So principal component analysis is something which we haven't discussed about yet. So this is going to be our first encounter with a unsupervised method. Now, the way to read what we are going to talk about now is dimensionality reduction. That's the key message. So autoencoders are actually ways to reduce the dimensionality of a huge problem. And it's a very easy thing to implement, because if you have written a neural network code, if you have a recurrent neural network code, or if you have a convolutional neural network code, you can use that as a basic part of the algorithm. Now, the third thing is that the autoencoders are going to function for us as the entry point to generative models. So when we are done with this topic, which will probably be before the Easter break, we are going to next week also to start preparing the ground for generative models. And autoencoders form one of these very popular methods, which are called variational autoencoders. So just to remind you, when we are dealing with generative models, what we are training then is a probability distribution. And that probability distribution can then be used to generate new instances of a specific type of problem we are dealing with. So if you train it on reproducing pictures of cats, you can then use the probability distribution to generate new cats for you. So that's the basic philosophy of generative models. And the autoencoders, together with Boltzmann machines, which will be the very, very first generative model we will encounter, which is a kind of a neural network. These are some of the basic elements of generative modeling. So we have at least three basic components which are of interest for us: the dimensionality reduction, which autoencoders give us; the link with a principal component analysis, which is actually something which dates back more than 120 years ago. So I think it was in the end of the 1890s that the first principal component analysis method was outlined. And the principal component analysis has been there as one of the pre-deep learning methods, and it's been used repeatedly as a way to reduce the dimensionality. So today, I think this is, from a pedagogical point of view, it's a very important link. And at the same time, it allows us to present one of the popular dimensionality reduction methods. So I hope you see the basic messages. So stepping stone towards the generative models, which will be the next part of this course. And then obviously autoencoders as a very popular method for imaging, fitting functions, and doing dimensionality reduction. So I have some reading recommendations, and Goodfellows, chapter 14 is actually a very, very good one. Many textbooks tend to be pretty superficial when it comes to autoencoders, and in particular also the link between principal component analysis and dimensionality reduction, what it means. Because when we have a neural network, it's much more difficult to actually see this connection, the direct connection with dimensionality reduction, which is essentially what an autoencoder is doing for us. So you will find some of these references here, and autoencoders have actually been there for quite some time. So you can view them as artificial neural networks. You can stack together feed-forward neural network, a recurrent one, a CNN, etc. And what you end up with is to have one part where you are encoding the information, and then you have a mid-layer where you try to extract some dimensionality reduction features, and then you decode it, and with the decoder you can then reproduce an output. So let me try to switch over to the whiteboard and give you a very, very simple example on how you can look at a autoencoder. So in the text you will find much more information. You can read some of this yourself. There's a lot of blah blah here when it was introduced, etc., etc. But the way we can look at this is as follows. So you can think of having two functions, one function f and one function g. So let's switch over to the whiteboard and try to visualize this and just slow down the pace that way. So let's switch to the whiteboard. So the way you can think of an autoencoder is in the following way. So you would have some inputs, and these can be a series of input variables. So you could have an x0, x1, down to some xn minus 1. Now, this part is then fed into a so-called decoder part, or encoder part. So this can be a feed-forward neural network, just to give you an example. So that's the reason why I'm putting H here to indicate that this is some kind of hidden layer, which does some black magic for us. And then to some m minus 1. These can be fully connected, or they can be sparsely connected. That depends on the way you set up this piece. Then there is a second part here, which is often called the code part. So you do some operations in here. And then there is a decoder part. And we are going to label that one with a specific function, which we just call for a function g here. So g0 down to some g of L minus 1. And then there is an output. And this output is something which we will label with some x0 tilde. And ideally, we would like to have as much output as we have inputs. So these are the different elements of an autoencoder. And the way you can view this now is as you having some kind of function f. So there is a h, which now represents the encoder part. And this is given by some w. And then we have some weights and biases, some parameters, which are now simply labeling with a w here. And then there is an input like this. Then what we have next is a part here where we have the decoder part. And that decoder is given by this function g. And this g depends on v. And it has as input this h. And this is then resulting in our x tilde here. So there is a way to think of this. And the way we are going to gauge whether the output which we generate is close to the input, because what we want is something which is pretty close to the input. So we can then define a metric. And the simplest form for metric which we can think of, if we are dealing with, let's say, a regression type of problem, is the mean squared error. So this metric could then be the mean squared error, which we then would label as a 1 over n. And then we have some sum from I equals 0 up to n minus 1. And then we have x of I, the input values. And then we have the output values, x of I tilde squared. And then we want to optimize this. Now, let's look at a very simple case, which is the one which we will link with principal component analysis. So let's assume now that there is a linear dependence. So you could think of you, instead of having a feed-forward neural network in here. So when I'm writing this piece here, this could be a complex neural network with many layers. But it could also be a simple perceptron model if we want to. So that means that we could think of a linear dependence. So suppose now that you make a very simple dependence, a linear dependence, as an example. So if we do that, what we could think of now is a problem where we have the minimization. We take as arguments these matrices W and V, and then we want to minimize this mean squared error. So this is the optimization problem at hand. That's 1 of x of I minus x of I tilde squared. So if we have a linear behavior, what it means then is that this function h, which now represents this hidden layer or the encoding layer, is now given by some unknown function multiplied with this input vector x. So this W could be a matrix, it could be the typical weights. I'm leaving out things like biases and all these other things, but I'm just making a simple assumption here. And then we could also assume that G is equal to some V, unknown parameters, times H. Okay, so if I do that, what I'm having then is a minimization problem of the following type of I equals 0 up to n minus 1. And then I'm going to have 1 minus V times W multiplied with x of I. And this quantity is squared. Because we see now that this x tilde, if we now write this as a vector, it doesn't need to be a vector. It could just be one value, just a scalar. This is obviously given by V times W times X. So what we have now, we have a way to encode the information here, which gives us some kind of transformation of the data. And then we have another way to decode the same information and then extract an output. Now, this approach which you see here is the one which will give us a direct link with a principal component analysis. So that means that you can view an autoencoder as a way to reduce the dimensionality. So in order for you to see this, let's now look at something which I've seen before, ordinary least squares. So to understand the dimensionality reduction, so let's look at that, dimensionality reduction. So the first example we are going to look at is ordinary least squares. This is ordinary least square. In that case, we are making a model where we have this x tilde, which is given by some matrix, and now I'm going to write this as an uppercase letter. And this matrix is called the feature matrix or the design matrix, multiplied with some unknown parameter theta. So this is our x. And this quantity is normally called the feature matrix. And in our case, this is a matrix which has a dimensionality, a typical dimensionality of n times p, where n is the number of samples we have, or the number of data entries. This is a number of samples. And this is the number of what we normally call features or properties. So the features, if you're thinking of this X now representing data about house prices. So you could have one column with a number of rooms, one column which has a price, one column in this matrix X, which then represents the number of bathrooms, etc., etc. So these are all the features which characterize the price of a house, just to give you a simple example. So many of you have seen this before, and it means that, and now I'm going to write this matrix X in terms of a set of vectors. So there will be a column vector X0, a column vector X1, and this goes all the way. So let me just correct this one. And this goes all the way up to X of P minus 1. So these are the features which define this matrix. Now, these vectors which you see, they are not necessarily orthogonal to each other. So you can have strong correlations in the data sets. So clearly you would assume that the price of a house is strongly correlated with the number of rooms. It may be strongly correlated with the size of the house. So there would obviously be correlations between these data sets. So this thing with correlations is something which I will bring up again and again, because when we come to the principal component analysis, this is actually where we are going to start in order to reduce the dimensionality of the problem. Now, if you use that, when you do the ordinary least squares, what you find then is that this theta, this is the optimal value. When you optimize the problem, this is given by this matrix X transpose times X multiplied with X transpose times Y. So everything here is known. So if you can invert the matrix, then you solve the problem. So the only thing you need to do is a matrix multiplication, matrix inversion, a new matrix multiplication, and then a matrix vector, and then you're done. Now, the thing which is interesting now is the following. So if you now look at this X tilde, sorry, I should actually, I'm a little bit, I hope you can see the difference between the different symbols. So I'm going to keep an uppercase letter here. And then this is the input, lowercase x. So what we have then is that this quantity, which is now given by this matrix, times this optimal parameters with a hat on top of it, means that we have now performed the optimization, which you see here. But now the optimization is done with respect to these values theta. Then you can see that this is given now by this matrix X multiplied with this matrix X times X multiplied with X transpose multiplied with X. So let's call this quantity here for A. So this is a new matrix. This matrix, if you do the mathematics, you will see that this one, that means this quantity here, has dimensionality P times P. X has dimensionality N times P, so that means that this matrix has a dimensionality of N times N. Now, what is happening when I look at this matrix? This matrix A has some specific features which are very interesting for us. So this matrix A, if I square it, sorry, it's equal to itself. Now, in mathematics and linear algebra, this type of matrices have a specific name. And this is why this link with dimensionality reductions is so relevant. What do we typically call such a matrix? They have a specific name, but they're also used for specific mathematical operations. Yeah, that's a projection matrix. And they're also called idempotent matrices. So that means that here, the column vectors of the matrix X, they actually define the projection which is taking place. But now you should pay attention to one thing. So I am going to remind you of this. So what happens now is that we are actually rewriting the new value X in terms of this matrix A times the previous value. This means that the column vectors of X, the matrix, the feature matrix, they are defining a projection of the matrix of the vector input X. So if you then go back to this optimization problem which we had, so we were then optimizing, so this argmin in linear regression, we are now optimizing with respect to this variable theta. And now in the expression here, I'm not going to have the value of theta because that's going to be an implicit dependence. This is going to be given as 1 minus a squared times x of I squared. So here I should be a little bit careful because I should actually write this as an I. Actually, there's a multiplication here. So the notation is a little bit sloppy. You should rather write it out in terms of a norm 2 product, which would actually be better. So I'm going to write this as 1 over n, and then I have 1 minus this matrix A squared multiplied with x, and this is the norm 2 of a vector squared. So then I can keep this matrix vector notation. And this is nothing but 1 over n of 1 minus a times x of 2. So if we now look back at the linear dependence, which we had in the autoencoder case. So back to the autoencoder. What we had then was a minimization with respect to w and v. And then we had 1 divided by n. And then we have now 1 minus. And then we had v times w times the original x, like that. So that means that we can now read this as a and this as a. And then a times a is equal to a squared is equal to a. So in a certain sense, here we have no dimensionality reduction. But just pay attention, because the matrix A, when we do ordinary least squares, we haven't reduced the dimensionality. You see that? But this is a simple case of the way we can think of a linear dependence and what these matrices V and W could look like. Okay? So the autoencoder in general, so suppose now you do something like a very simple perceptron model where you have this linear dependence. Then this would be totally equivalent either to what we are doing now with the ordinary squares, or when we now come to the principal component analysis, we can actually reduce the dimensionalities of this matrix A. And I will show you an intermediate example with the singular value decomposition so that you have a clear understanding of what is going on. But keep in mind that when we do a neural network, this kind of linearity is not there anymore. So that means that in principle, this will represent non-linear transformations of the original data. And that is why the autoencoders are so much more powerful than just a linear decoding and encoding. Okay? So this is a typical example where we have no dimensionality reduction. So this is, in this specific case, there is no dim reduction. Now, I'm going to bring in a new example, which some of you have seen before, and that is the singular value decomposition of a matrix. And the reason why I bring this up is that this will become useful when we are doing the principal component analysis. So this is an SVD. And the SVD is, I mean, those who know me, you know that this is my favorite algorithm in linear algebra. You can do anything you want with a matrix, with the SVD. So if you now take this linear regression problem with ordinary least squares, where we had this theta optimal, which is given by this matrix X transpose times X. I'm trying to make this boldface and multiply with little x, the input value. Now, ordinary least squares means that you will actually have to be able to perform a matrix inversion. So if you have strong dependencies between these column vectors or row vectors, then clearly the determinant will be 0. You will have an eigenvalue which will be 0, etc., etc. However, with the singular value decomposition, you can perform this calculation of the inverse with a pseudo-inverse. But in general, you will actually use other methods like ridge regression or lasso regression. But if you look at this matrix X transpose times X, this is a matrix which we can singular value decompose. When we do the singular value decomposition, we can reduce the dimensionality of the problem. So keep in mind now that this has a dimensionality of P times P. So the original matrix, I'm just repeating this dimensionality. So the original problem has n data points and P features. So the matrix is in general not a square matrix. And in general, it's not, even if it's a square matrix, it would not be symmetric. But the general case is a matrix where the typical case, which we often encounter, is that n is much, much larger than P. So you can have a survey of 10,000 patients, and you are surveying properties, let's say about some specific tumors, and then you would have 30, 40 features, P. So that means you would have 10,000 much larger than 30, 40. If you, on the other hand, are doing a genetical analysis, then the markers of on the DNA can be millions. So the features can be million in the type of millions, and you have surveyed something like 10,000 patients. So that would be a case where P, it can be much, much larger than N. And many of these methods then, they become impractical because you have too large dimensionalities. Now, if you now look at the singular value decomposition, what you can do then, if you take this matrix xt times x, you can decompose that one in one orthogonal matrix plus a diagonal which contains the so-called singular values multiplied with a new orthogonal matrix. So let me just quickly remind you. So I'm not going to go through the proof for the singular value decomposition. I'm going to state it because we're going to use it. And then you will see how we can perform a dimensionality reduction. So what we have then, if we now look at this singular value decomposition, is that the matrix U, if these are real matrices, this is an orthogonal matrix. So that gives us the unit matrix, and that has dimensionality n times n. The matrix V is also an orthogonal matrix. So that means that the vectors, the column vectors, are all orthogonal vectors. This is a matrix of dimensionality P times P. It means that U of I times U of J is equal delta Ij. And similarly, if I take V of I or V of J, these vectors are also orthogonal. And we can rewrite these matrices in terms of these vectors. So I would have a U0 up to a UN minus 1. So these are just the column vectors, just another way of writing the matrix in a more compact way. I guess you're all familiar with this kind of notation, right? The matrix D, on the other hand, contains what we call the singular values. So that matrix could now contain sigma 0, sigma 1, and then it has non-zero values up to the rank of the matrix. And then we have zeros. So these are zeros. And these eigenvalues, they can be sorted. So you can decide whether you want to have them in as an ascending series or as a descending one. This is up to you how you sort the eigenvalues. Actually, these are called singular values. So sigma 0, it's pretty common to sort them like this. Sigma 1, etc., up to sigma p minus 1, and they are all larger than 0. So that's a very important property here. So you may ask, why are we doing all this? We are doing this because this gives a very nice link with the concept of dimensionality reduction. So let's now look at So I almost tore down one of the screens on the podium here. So let me just fix that one. Okay. So if we now look at a typical example of this matrix, just to give you an example of what this D could look like. So you could look at the matrix D, which is given by 2, 0, 0, 1, 0, 0. So in this case, D is a matrix of dimensionality 3 times 2. What you will see if I take D transpose times D, that becomes a 2 by 2 matrix. And that will have only non-zero values along the diagonals. If I, on the other hand, if I do D times DT, this is going to be a 3 by 3 matrix. It will contain 0, a 4, and these values here, but then we will have a row here with only zeros. So where does this lead us? So let's go back to the ordinary least squares now. So what we have is that X transpose times X is now given in terms of this U times D times V of T. Then, if I now look at my X tilde, that is given in terms of the matrix X divided by, or the inverse of the matrix X again, transpose times X, X of T times X. So let's now just use the singular value decomposition and rewrite it. So if we do that, we can rewrite this as the matrix U times D times V transpose. And then I have in the denominator, I would have V times D transpose times U of T times U times D times V of T. And then I have the transpose of the matrix. So I have a V of dt times U of T multiplied with a vector. So I should try to squeeze that in here, like that. So that's the original input which we had. Now, if you now look at this problem which we have at hand here, this matrix here, this final matrix, is a matrix of dimensionality P times P. This here is simply given by the identity matrix. So that means that what I get is a U of dt of V of T, and then I have divided by V, and then I have this dt, which we know is just a P times P matrix, times V of dt times U of T multiplied with X. That's our output. Now, if you look at this now, there is a linear algebra gem here, which I'm going to state again. And this simply states that if A and B are square matrices and invertible, each of them are invertible, are square matrices and invertible, and invertible, then there is a very interesting property which we have. So if you then have 1 divided by A times B, that is actually given by B inverse multiplied with A inverse. So that's one of these kind of linear algebra gems, which are hidden there somewhere, but which are extremely useful in this context. Now, what we know now is that V is a square matrix. It's also invertible because it just is composed of orthogonal vectors. So it's a square matrix and invertible. Invertible. The matrix dt of D is also a square matrix and it's diagonal. So this is just simply these values sigma 0 squared up to sigma p minus 1 squared. So I can now write this matrix denominator which I have, which is V of dt of D times V of t. I can actually rewrite that as a matrix dt, this square matrix, times V of t, which is a new square matrix, which is invertible, times an invertible matrix. And then I can rewrite everything. So that means that what I get then, when I place everything in here, I would then get that this x tilde is then given by u of d times vt times v. So remember, just let me give you another thing here so that you have everything. Since we have v of t of v is equal to the identity matrix, that means that v is simply given by the transpose inverse here. So this is just a linear algebra exercise. So then I would have dt of d, and then I have v of t times v. So these are also given by the identity matrix, multiplied with u transpose times x. Now there is a very important thing you have to note. There should be a dt here. So note now that this matrix which you see here, that has dimensionality n times p. This one has also dimensionality p times n. This whole thing here has dimensionality p times p. And keep in mind now that this guy here has zeros, but we are multiplying the zero parts of the dimensionality larger than p with something constant, so that just gives us 0. So that means that when I write everything out here, I can actually show that it's pretty easy to see that I can have a summation from I equals 0 up to p minus 1, not n, where I have now the vectors u of I transpose, and this is multiplied with x. So with the SVD, we have a projection with p degrees of freedom. So this is no longer, because U, the matrix U, is a dimensionality n times n, but we're only keeping the terms where the singular values are non-zero. So we've made a projection of the number of degrees of freedom here. Now, the thing which we want to do now is actually to we want a value n which is smaller or equal than p, so that we can reduce the number of features to the essential ones. So the principal component analysis is such a method which allows us to truncate this expansion over p with a value n which is smaller than p. So we find such a value. So obviously when I ask the question, then yes, principal component analysis is one of the ways of doing that. Now, if you think back to the original problem which we had, so let me just spool back a little bit. If you think of standard ordinary least squares, when we did that, then we ended up with a projection on the full input data with no dimensionality reduction. So we were operating with a matrix which has a dimensionality n times n, which is equal to the number of data points we have. Now, when we are now doing an SVD, we have another type of dimensionality reduction given in terms of the orthogonal vectors of a singular value decomposition. But if we use the standard ordinary least square result as here, we have demonstrated here that we have a slightly different ways of doing the projection. Now, if you now go back to this equation here, what you have in this specific case is that this V would be U and this would be U of T here. So this is just another way of performing the encoding of the data and then projecting down. So if you now look back at this singular value decomposition, I don't know if you remember that image of that city in Italy, where I used the singular value decomposition to reduce the dimensionality of the image. So the thing with the SVD is that I could say now that, okay, let's suppose that P is equal to 10,000. In that example which we had, I wanted to reduce that. I reduced that down to 5, and then we increased it slowly so that we're getting closer and closer to P. So for every time we reduced the image, we had a encoding, which is the singular value decomposition, and the decoding was a truncated dimensionality. And that gave us an X tilde, which was a blurred image, if you remember that example we looked at. So I think we started with, I think it was not 10,000, it was 1,000, which we had as a dimensionality. And then we looked at how we could reconstruct that image with only 5 vectors U. And then we increased that dimensionality to larger and larger numbers of vectors till we actually hit the final image. So we could have a blurred image which we could store, but somewhere we would need to have the information about the singular value decomposition. So clearly, if you have lots of data, this becomes unwieldy. It becomes quickly untractable. So, but the basic message is that one. So if you think of this kind of dimensionality reduction, which is done by a autoencoder, if you now keep in mind this singular value decomposition of an image, which was a traditional method of decomposing an image, you could now think of performing the SVD. That is your encoder. Then, in here, you perform an operation where you decode by reducing the dimensionality of the vectors you keep. So if you had 1,000 inputs, 1,000 vectors, which were produced by the singular value decomposition here, you could keep 5 of them, and that would give you that blurred image as output. Then clearly you could reconstruct it better and better by having more and more information in the decoder. But you see, this is essentially the basic message of an autoencoder. And if you're now dealing with the linear transformation, the decoding and encoding as a linear operation, where you have a matrix times a vector, then we can show that this is the same as principal component analysis, which is a dimensionality reduction method. So the 2 examples I showed you now are just ways of thinking of these linear encoders, W and H. But in general, we end up with a neural network consisting of making up the encoder and also the decoder. And then we would train the parameters there by standard backpropagation. So I hope you see the kind of major picture. And then after the break, I'm going to say something about the general structure of an autoencoder. So if you have a neural network code, you can actually make your own autoencoder. And then we are going to look at some of the general features, and then we are going to link with the principal component analysis and show that this is indeed a real dimensionality reduction. So the examples I gave you now was more to motivate what is coming after the break. Okay, should we take a small break? So as we discussed before the break, this is something which typically defines the setup of an autoencoder. So before we move into the PCA, I wanted to say give you some kind of generalities. And then next week, we are going to look at how you can implement this in Keras with TensorFlow. In the textbooks, which you have access to, both the one by Foster and Rush et al., you will find examples using PyTorch and TensorFlow and Keras. So there are tons of examples out there if you want to use them. And these autoencoders are used both for the regression type of problems, you fitting a function. So you could take the differential equation solvers, which some of you have been looking at, and actually feed that one into an autoencoder. So it's fully possible. Alternatively, if, as many of you are interested in classification problems, autoencoders have been widely used in classification problems. So the typical schematic output is something which we now can decode in typical architecture. So in most architectures, the encoder and the decoder are typical neural networks. And they can easily be trained with existing libraries such as TensorFlow, with Keras and PyTorch, etc., with backpropagation. So the backpropagation algorithm pops up again and again, as we have been discussing throughout the semester now. And then, in general, as we said, the encoder can be written as a function that will be dependent on some parameters. And then the same thing applies to the decoder part. You have a new function which then can be used to the decoding part. And the whole idea is now that these dimensionalities, Q and N, they could be the same, but ideally this Q should be smaller than N here. And then at the end, we try to optimize with respect to the parameters which enter these functions F and G, and we have some functions which we want to minimize. And the typical function is then a typical mean squared error. It could be a cross entropy and other types of functions. I'm just coming back to this. So the standard setup is normally a feed-forward neural network. It's often called a feed-forward autoencoder. And typically the first layer has a number of neurons, which equals the size of the input observation, which means that if in case you're dealing with images, this can actually be a pretty large dimensionality of the first hidden layer. So this is something to think of. And for regression type of problems, this is often a little bit easier. But as you move towards the center of the network, so the center, you've done through the encoding part, and then you're starting the decoding part. And typically the middle layer has the smallest number of neurons. This is often called the kind of bottleneck. And you understand that easily if you go back to the image here. In the middle here, that's where you have the smallest number of neurons. And you see typically you get something which gets smaller and smaller, narrower and narrower. And that's often called just a bottleneck, by obvious reasons. And the typical feed-forward layer would be something like this. You have an encoder part, and then you have some feature-generating layer, and then you have the decoder part, and then you have the reconstructed input. So if you think back of the standard linear regression, where we have this matrix A squared, in that case, you would have an encoder part, which is just identical to the decoder part. It's just a matrix A times a matrix A, which again then represents a projection of your original data. It's also pretty common that the layers after the middle one are mirrored version of the layers before the middle one. So an encoder with 3 layers could have the following, could have 10 nodes, and then 5, and then 3, and then 3, which is equal to 10, where the input dimensions is equal to 10. And all the layers up to and including the middle one make what is called the encoder. And all the layers from from and including the middle one up to the output make what's normally called a decoder. And if the feed-forward neural network part or the feed-forward autoencoder is successful, then you will have a good approximation. What is essential to notice is that the decoder can reconstruct the input by using only a much smaller number of features than the input observations initially have. That is the hope. So I'm going to skip some of these typical activation functions which are used. So keep in mind now, if you go back to this drawing here, if we take the general one, which we had here. So what I want you just to keep in mind is that if we have this linear dependence, which we discussed before the break, then we can link directly to an understanding of dimensionality reduction, like we did with the singular value decomposition. But if you now play around with a standard feed-forward neural network or a CNN, it's much more difficult to see the mathematics of that. So this is one of the reasons why we often, when we discuss autoencoders, you will see this linked with a discussion of the principal component analysis, just to give this kind of overarching understanding of what it is doing. Because as soon as you bake in a feed-forward neural network, you know the basic mathematics, but it's much more difficult to actually see the big picture from that. Because you cannot, when you have all these non-linearities baked in, it's difficult to see immediately that this corresponds to a dimensionality reduction. So if we just scroll down a little bit, so the typical functions which you use, it is this ReLU and sigmoid, and the ReLU function, that means in the output layer. So the ReLU function is often used for the type of regression problem. And one of the problems with the ReLU function, as we can see here, that's defined for values from 0 to x, but you could have an input which is negative, and then it's pretty common to replace that with what is called the leaky ReLU function. And these are typical activation functions, but you can play around with different types of activation functions. So if you're dealing with a classification problem, then it's pretty common to have in the output layer a sigmoid function. And typically the MNIST data set, which we have encountered many, many times, is a data set where you, and the examples which you will find in both my lecture notes and many textbooks actually based on that. This is a set of data which you would often scale because your pixels can take values between 0 and 255. So you would typically scale them, and I don't know if you remember, but in some of the examples you will see the pixels being divided by 255, so that you scale your data between from 0 to 255 to 0 and 1, which is a typical range of arguments which a sigmoid function takes. So that's a pretty common way of scaling your data. Then, if you look at the cost-loss function, this is a pretty common one if you're dealing with a regression type of problem. And if you're dealing with a typical problem of the type of a classification problem where you have either 0 and 1, a binary classification problem, you would have a sum over the data, a sum of the features, and these xij's would then correspond to the features as columns and I as the input variable or the data samples. So these are typical functions which are being used in a setup of an autoencoder. But keep in mind that you can play around with different types of activation functions and different types of cost-loss functions. So what I wanted to do now is actually to link what we have with the PCA, with the principal component analysis. And I wanted to give you first a kind of to look at the basic. Okay, so let's switch back to the whiteboard. Now let's just bring this up. So the topic now is dimensionality reduction, dim reduction, and PCA. So if we now look at the PCA and think back at what we did, what we can say now, if you look at this reconstruction error, which we defined before the break, in terms of the mean squared error, what we would like to have now is an approximation where we have our x minus v times w times x, norm 2, and we want this to be given by a small number. And the PCA, or principal component analysis, tells us that we can satisfy this constraint with a dimensionality which is smaller than the full dimensionality, so that we can define this quantity n, which is smaller or equal to p, the number of features, and in a specific way. So let's try to understand how the PCA can be used to actually find this quantity n. So the question is, how do we define n? The way we are going to define n is in terms of the variance of the correlation matrix or the covariance matrix. So we need to introduce some basic mathematics. So let's basic elements. Of a PCA analysis. And then with these basic elements, we can set up a recipe by which we can now find this reconstruction error within a specific parameter epsilon here. So which we can say now that, okay, if we have a reconstruction error less than, let's say, 95%, or gives us 95% of the whole data we want to reproduce, what kind of constraints, so how can we constrain this variable n here? So we want to reduce the dimensionality. We don't want to have all features. So this is something which has been used in machine learning calculations in order to reduce the dimensionality before you apply a method like a neural network or a convolution neural network, etc. So what you're doing then is to find which data are the most important ones. So in genetic analysis, where you can have millions of features, by diagonalizing the correlation matrix, you can find out that perhaps it's only 100 features which are important for classifying a specific problem. And that means that you would go down from millions down to a few hundreds, and you would use these features only. Now, these features are not directly linked with the explicit features we had previously, because you're diagonalizing a problem. So there will be a new eigenvector, which is a linear combination of the given features, but then you would look at the components of these eigenvectors and then pick the largest components. That's the way you would typically use in order to reduce a dimensionality. Because just think of it, if you're dealing with a neural network with millions of features, I mean, it's going to take an eternity or to basically be impossible to train it. So we have to do some pre-screening of the data. And this is an unsupervised method because we don't know which features are the essential ones before we have done the calculations. So you can think of the PCA as a dimensionality reduction method, which is unsupervised in the sense that if you have 1 million features in a genetic analysis, and you reduce this down to 100, in the beginning, you didn't know which 100 ones are the essential. Okay? So let's look at the basic mathematical elements of the PCA. So we have an input, x, so the feature matrix or the input matrix, which we label with this uppercase letter X. And this is something which has a dimensionality, as we discussed before the break, of n times p. So I'm using the rows to indicate the number of samples. So this could be the number of patients you have been surveying, or the number of people in a genetic survey. And p could be the number of DNA properties which you're interested in. Or it could just be features which characterize a house you're selling. So the quantity we want to look at now is the covariance. But let me also quickly remind you that this is now given by a matrix where each column represents a specific feature up to an x of p minus 1. And these vectors are not necessarily orthogonal. So there can be correlations between the data. And this has always been one of the problems with ordinary least squares, that you can actually have a feature matrix which represents strongly correlated data. And then you cannot invert the matrix in ordinary least squares. Now, there is a quantity which I'm going to define for you, and that's called the covariance. So the covariance between two of these vectors, so this is a vector xi, and a vector, I'm trying to make this boldface to indicate that these are vectors. So this is defined as 1 over n, and then I have a sum over k, and these are the data elements which we have, the rows of the matrix. So we have a row xk of I minus xi, the average value. So I'm going to define these quantities in more detail. And this is multiplied by xkj minus xj. So the x of I is now the mean value for each column. So it's a sum over xk of I. So just to remind you that the vector x of I is just given by x0i, x1i, and then all the way down to xn minus 1 of I. Okay? So what is common to do now when you have this quantity is, so let me just put that as an aside, that is to center the data. Now, I mentioned just now in connection with images that you would scale the images, since you have the pixels represented with number from 0 to 255. You would scale that by dividing by 255. But in general, what you do normally with the data is to scale and also center. So center means that you have subtracted the mean value from each column. This is often done in order to avoid some specific dependence on outliers. So it can reduce that one in the fitting process. So it's pretty common to scale your data and center the data. So those of you who have taken a course in machine learning know that these are some kind of default procedures you do on the data before you start doing anything. So sometimes centering is just lumped together into kind of generic wording, scaling. But actually centering means that you subtract the mean value. So I guess most of you are pretty familiar with that, but I just wanted to repeat it. So that means that when you look at this xk of I minus the mean value, this defines some xk of I tilde. But in order to avoid the confusion, I'm simply going to relabel this as x of k of I. Okay? So from now on, all the data are centered. So all data centered. And this is a common pre-processing of your data set before you do anything. So if you then look at the covariance, suppose we have a simple example here. So we have a vector x, or the matrix, which now could be given by a very simple case, 0x1, x11, and zero, and x20, and then I have x01, x11, and then x21. So suppose these are the vectors. So this would be x0, and this would be the vector x1. Then I can calculate the covariance. So if I do the covariance between the vectors x0 and x1, this is simply, so I have 1 divided by the number of elements, which are 3. So I would have 1 divided by 3. Normally what you would have is n minus 1. That's the, if you're using NumPy or any of the Python libraries, whether you use pandas, etc., it actually calculates the covariance with a factor of 1 divided by n minus 1, because the mean value is not an independent quantity. So we have x00, x01, plus x10, x11, plus, so I hope you don't find this too boring, but I do this because I wanted to show you that this is the same as x0 transpose times x1, multiplied by 1 over n. So that means that I can define my covariance of the whole matrix. So the covariance of the matrix X, which actually is the same as X transpose times X. So when I write covariance of the matrix X, or the feature matrix, that is the same as us calculating 1 over n of X transpose times X. And this has a dimensionality of P times P, the number of features which we have. So if you rewrite this one for that simple case with 2 features, P equal to 2, then your covariance X is equal to 1 divided by n. And then you have x0 of x0, and you have x0, x1, x1, x0, and x1. And what you can show then, so if I now write sigma I squared with 1 divided by n as the sum over k of xk of I, so these are the scale data. Remember now that it's centered, so I've taken away the mean value. So the variance is given by that. So that means that these terms here with that one, the diagonal ones, are just the variances. And then if I have independent and identically distributed variables, so suppose the inputs here are given by stochastic variables, and they are identically distributed and independent, then the covariance is exactly equal to 0. And then we can just read off the covariance matrix as the diagonal elements, which are then the variances, which tell you about the deviation from the mean value. So that's just a measure of the deviation from the mean value. So if I do that, if I use that, then I can show that the covariance matrix is simply given by the variance along the diagonal, and then this matrix is actually symmetric. You can easily see that when you set up the expression for the covariance. So this is x1, x0. So in general, you could set up this in terms of all the non-diagonal elements would be the covariances between the different vectors which you have in the matrix X. So this is a covariance matrix. And now one thing which is common to do, since the variance and the covariance can become very large, it's common to scale them. So what you will often see then is that you will see the correlation matrix, which has elements which are given by the covariance of two vectors, xi and xj, divided by the square root of the variances. So it's just a way to scale the data because the covariance and the variance can take very large values. And that means that the correlation matrix is then a much simpler matrix. So it has diagonals with 1. And then you would simply have the correlation matrices. And I'm just writing this in a more generic way. So you would have this block. And since it's symmetric, you would see this block here as well. So this is a quantity which is often studied. Now, I introduced the singular value decomposition in the previous lecture, simply because I'm going to reuse it now, because there are some nice features which we can look at. So let's bring back the SVD. So what we said then with the SVD is that we can perform the singular value decomposition. So we have an x transpose times x multiplied with 1 over n, which is the covariance matrix. So the covariance is interesting in terms of the PCA because that defines the variance of the variables which we have. And we are going to use that as a measure to make the truncation in dimensionality. Now, if you then look at this matrix x transpose times x, and we make an SVD of that. So suppose now we take x and perform the SVD. So we know that this product is a P times P matrix, the features which we have in the problem. So then, just to quickly remind you of that, so the D matrix contains the singular values. Some of them can be 0. So if I look at my covariance matrix now, that's covariance of x with, I should write with SVD. So let's do that. So we have 1 over n, and then we get V of D transpose times U transpose, and this is multiplied with U of D of V of T. This is nothing but 1 over n. So this is given by the unit matrix. So we have a V times D of T times D times V of T. Okay, so this is a matrix. Just keep that in mind, eh? Now, what we have is a matrix V, which contains orthogonal vectors. So let's now look at this specific matrix. So if we now think of x transpose times x, and we multiply that one from the right, with V, that is going to be equal, well, this quantity here, let's just keep this 1 over n here. Then we have a V of D, and I'm writing this as a D squared of V of T times V. So this is the same as 1 over n of V of D squared. Now, D squared is a diagonal matrix, so that means it commutes with V. So I could multiply it with V on the left or the right, doesn't matter. So what I have now is that if I pick a value, so if you remember that V is simply given in terms of these vectors, V0, V1, up to V of P minus 1. Then I can rewrite my covariance matrix in terms of x transpose times x times V of I. And that is going to be given by V of I multiplied with the singular value squared. So if I have performed a singular value decomposition, it means that the eigenvalues, so the eigenvalues of the covariance matrix are the singular values of the singular value decomposition of the matrix X. And that's a very neat result. So that means that the eigenvalues of curve V are the singular values sigma I squared, or the singular value squared, with eigenvectors. And this is an extremely powerful result, with eigenvectors V of I. So this means then that if I now want to diagonalize the covariance matrix, and now it's where we're going to make the link with the PCA, can we find a set of orthogonal transformations which keep most of the variance? So what we are going to look at now, if we look at the sum over the total variance, so the total variance so I'm taking the variance of all the features is the sum over all these variables sigma y, from I equals 0 up to p minus 1. So the PCA, what that is doing is that is constructing a set of orthogonal vectors without having done the singular value decomposition. So the PCA constructs a set of orthogonal vectors and I'm going to call this set for S. There is a matrix, an orthogonal matrix with a vector S0, S1, etc., up to some SP minus 1. So this matrix S will diagonalize the covariance matrix. So if we take this matrix S and we multiply that, this is the standard way by which we would perform these operations. And you know that the covariance, this S, is put outside here. So that will give us the covariance of Y, which is diagonal. Which means that the data are not correlated anymore. Can we construct such a matrix S iteratively so that we can actually put a truncation on the total variance so that instead of having a sum over P, we have a sum from 0 up to a variable n minus 1, where we have sigma I squared is smaller than a truncation of the total variance. Truncated total variance. So keep in mind now that S is a matrix. So when you diagonalize, so just a quick reminder, when you're diagonalizing a matrix A, and you have an orthogonal transformation, that gives you a diagonal matrix. So there is some magic expression now which diagonalizes your matrix. And this matrix S is not a stochastic quantity because we have finite rotations which are made. If you think of Jacobi's method in linear algebra to find the eigenvalues, that is given by a predetermined set of cosine and sine rotations around. So you have a rotation around an axis where you zero out the non-diagonal elements. And at the end, when you perform many such operations, you have a matrix which is fully diagonal. So in the PCA, what we are doing then is actually to construct these different matrices, these different vectors S, so that we build up the variance. And then the question is, can we make a truncation in terms of these vectors so that we still have a large enough part of the variance? So what you will often see when you diagonalize a covariance matrix, suppose you have a 100 times 100 matrix, in case 90% of the features are very uncorrelated, you will see that there may be only 10 features which dominate. So these dominating features could then give you 95% of the total variance. And then you would say that instead of me making my neural network calculation with 100 features, I do a truncated calculation with 10 features. And if then your final result comes out pretty well compared to the results you want to reproduce, then you would say that, okay, this dimensionality reduction is pretty useful. And that allows me to speed up my computational efforts. I can get a decent result, which I can live with. So the PCA deals actually with building up. So it's a little bit, how to say, I hope you can see the wood for the trees here, because I started with the exact problem as you would do with a singular value decomposition. So if you can perform the singular value decomposition, then from that one, you have the eigenvalues, which are the variances. And then you can say that when I look at these values, I now pick the largest ones, the 10 largest ones. And if they give me 95% of the variance, I'm happy, if these are the 10 largest ones. But this means that you have diagonalized a large matrix. So in this kind of genetic problems, what you would do then is to, if you want to diagonalize it, you could have a matrix, the covariance matrix, which could be 1,000,000 times 1,000,000. So diagonalizing that one is something you would have to deal with iterative methods. And then when you diagonalize it, maybe you figure out that there are only 100 features, which are the essential ones. And then you can reduce your problem from 1,000,000 to 100. But in doing that, it means that you either diagonalize or you perform a singular value decomposition. Now, the reason why I brought up the singular value decomposition here is because then you can see directly that the eigenvalues or the variances are the singular values of a singular value decomposition. So that's a very nice mathematical link. But when you want to do the PCA, with the PCA, you're constructing these vectors V of I iteratively. And then every time you have a new vector, you optimize the reconstruction error. So let's see how that goes on. So when you look at the PCA, what you're doing then is to define a so-called reconstruction error. And that reconstruction error is something like this, which is now given by 1 divided by n, and you have a sum over all these quantities. And now let me just rewrite this in terms of just a vector matrix relation here. So what you would have would be something which looks like, well, let me just put that up. So you would have x minus, and then I have a matrix. This is the first one. So we are going to build up these vectors S iteratively. So you could start with just one vector for all the data samples which you have, multiply with x, and you want to optimize this quantity. So what you would start optimizing then, so this is the reconstruction error, which you want to use in the optimization. And the way you would proceed then would be to assume that there is a Lagrangian, which you can set up. So you define a Lagrangian, which is given by some transformation, S transpose, times your covariance matrix times S0 plus lambda 0. And then this has to be normalized and orthogonalized. So this is a typical problem you would start with in order to define this. What you ideally want, so you're not limited to only S0, because every one of these is going to give you a value for the variance. So if you now look at this quantity here, when you optimize with respect to S0 and this lambda 0, what you find then is the following. So when I do the optimization, I take the derivative with respect to S0. So this is the first derivative which I'm taking. Then I would get S0 is equal lambda 0 times S0. Then if I multiply from the left with the S0 transpose, what I get then, S0 transpose times the covariance of X times S0, that is simply lambda 0, because I put the constraint that it has to be normalized. And this is what we found from the singular value decomposition. It's the first eigenvalue. So that's the variance. So when I perform this transformation, I actually have the variance of the component S0. And now I'm assuming that this is the largest variance. So what I want to do then is actually to optimize a series of such vectors. So I would typically start with an S0, my first vector, which is going to give me the largest eigenvalue. And then you would continue by induction. So you could take the next eigenvector, which is S1. And then you have a new Lagrangian, which is the function you want to optimize with respect to the parameters. So you have a covariance. So let me just set up this of covariance of X of S1. Then I have the eigenvalues, which I want, S1 transpose times S1. But then I need a new parameter, which simply requires that S1 transpose times S0. So I want to have the orthogonality with a new vector. Then I have to take the derivatives with respect to these quantities. Derivatives with respect to lambda 1, gamma, and S1. These are the quantities I want to optimize. So two of them are so-called Lagrangian parameters, lambda 1 and gamma. Are you familiar with Lagrangian multipliers? You may have seen some elements of Lagrangian calculus. Who has never seen Lagrangian calculus? Okay, so that's a kind of trick which you often use when you're having problems you want to optimize. And then you have constraints that there should be orthogonality. And then you want to find these vectors S1, which then diagonalize this matrix. So if you take the derivative, if you look at the first term, you're going to get a factor of 2 because you have S1 transpose times S1, and that applies to the second term as well. So if we divide with 2, if I take the derivative with respect to S1, what you get then is a covariance of X of S1 plus a gamma divided by 2 of S0, and that is given by lambda 1 times S1. And now you multiply with S1 transposed on both sides. So you do that. Plus gamma half of S1 transpose times S0. This is imposed to be 0. When you take the derivative with respect to gamma, that leads to this relation being equal to 0. And this is equal to lambda 1 times S1 times S, which you have required to be equal to 1. So then you can find again that S1 of t times the covariance of X. This is a new vector, where S1 is equal to lambda 1. So if you do the singular value decomposition, this should actually be V1, which corresponds to the second largest eigenvalue. So I won't be able to finish this in time, but I'm going to wrap this up next week. And then we're also going to go back to examples using autoencoders and how we can, what kind of results we can expect. And then we are going to start making the bridge with generative models. So the autoencoders are forming the basis for something which is called variational autoencoders, which are unsupervised methods, but of the generative type. So next week, at the end, we are going to try to make the bridge between the discriminative models we've been dealing with now with generative models, where we can actually generate new data from a probability distribution. So I will conclude the proof here of the PCA next week, and then we're also going to look at the concrete, explicit examples.